Hello dear students, in the last class we have to discuss the basic properties of a group, and today now we have to discuss some problems on the elementary properties. So let us begin with the first problem. If G is a group and A and B are the element of a G such that B can be written in the form of a X inverse for some X is equal to this belongs to G, then B to the power n is equal to X A to the power n X inverse for every integer n in Z. We solve this problem because we have to every integer is this, so all possible cases are there for integers. We divide this problem into the three cases. We have take n is equal to 0, we take n is greater than 0, we take n is less than 0, and in all these three cases if it is true then we can say that this is true. So if we take n is equal to 0, then you say that b to the power 0 is equal to, we have a identity element, and now from this side we can say that we have to take b is equal to 0. So you have a x A to the power 0 and x inverse. This can be written in the form of a x identity and we have a x inverse is equal to x inverse is equal to identity. So we getting this b to the power 0 identity and x, this also is equal to identity. So we can say that simply b0 is equal to, we can say that is equal to x A to the power 0 and x inverse is there. So in the case of n is equal to 0, the result is true. So case 1 we have n is equal to 0, so this means trivially for the case of n is equal to 0 it is true. Now we have to try to discuss for the case for n is a greater than 0 and is a positive integer. So for positive integer we prove the result by induction on n. So the result is hold for n is equal to 1. Obviously you can just say that you have a, we can say that b to the power 1 is the same as x e to the power 1 and you have a x inverse is this. For n is equal to 1, so b and we can say simply this is a trivial case. For n is equal to 1, b can be written in the form of x inverse. So this is trivial such that we have by the given conditions into this form. We assuming that let the result hold for n is equal to m, and so that result is hold for m is equal to n means b to the power m is equal to x A to the power m x inverse. Now we have to try to solve this for result is true for n is equal to m plus 1. If the result is true for n is equal to m plus 1, then by the induction hypothesis we can say that result true for each and every positive integer n. So let us begin with b to the power m plus 1 can be written as a bm into b, and then we can say that b to the power m is x A to the power m x inverse x, and b is equal to, we have x A x inverse, and we use the associativity here. So we can say x A to the power m x inverse x A x inverse, and so this we can write into this form. And now x inverse is equal to, we know that the identity element, so this can be written x A to the power m identity x A x inverse, and if you have to this identity element, this is, we can say that this is again giving you a, so this is written as x A to the power m plus 1 x inverse. So if we have a b to the power m plus 1 can also written in the form of a x A to the power m plus 1 x inverse. So we can say that the result is hold for n is equal to m plus 1, and the induction is complete, and thus the result hold for every positive integer. Now we have a third case. In the third case we have to discuss that result is true for n is less than 0, so n is a negative integer, so we can say that then if n is a negative integer, we take n is equal to minus m, and m is a any positive integer, m is greater than 0, we have to assume that. Now we have to prove that this is b to the power n, and then b to the power n can be written as b to the power minus m, and then we know that the exponents property b to the power m is equal to b to the power m to the inverse, and b ki power m is can be written as a x a to the power m and x inverse ka whole inverse. Now we use here the property of this ab inverse is equal to b inverse a inverse. So this is which can be written in the form of x inverse to inverse, then am to the inverse and x inverse to the, and then again the property of this a inverse to inverse is equal to a. So this is come to the x, and we have to just say that a to the power am to the inverse is the same as a to the power minus am, and then x inverse are there. And so a to the power minus m is equal to n, so b to the power n can be written as a x a to the power n x to inverse. So ultimately we show that if x we can show that if we have a b can be written as a x a to the x inverse, then b to the power n x a to the power n x inverse for all integer. So combining all these three cases, we get b to the power n is equal to x a to the power n x inverse for all n belongs to the z. So I think it's a very clear this examples. Now we have to move to the another problem. Let G be a group such that ABC belongs to the G, and the condition is giving AB is equal to CA implies that B is equal to C, then G is abelian. So this is not exactly the cancellation law, cancellation property, but this property is called is a cross cancellation law, because in the cancellation property we can say that AB is equal to AC, then it implies that B is equal to C, or BA is equal to CA implies that B is equal to C. But in in this case, this is giving that if AB is equal to CA, then we have to imply B is equal to C, then we have to show that G is abelian. So G is abelian means we have to using the we have to show that means any two elements A and B are the element of a G, then AB is equal to BA. We have to prove into this way. So we take a this A and B are the element of this by the associative property A, B, A. This is we can write in the form of a ABA, and then you can see that this can be written in this form by the property of this. This is A, and this is another element, and this is you have a this is working as a C, and that's A. So we can say that by this given property, we can say that by the given conditions BA is equal to AB, and then so that G is a and G is a abelian group is there. So this is G is abelian. We can simply that this is very trivially we can say that if this cross cancellation law hold, then G is a abelian this thing. Okay, this now we have to move another problem, and that problem is this: if G is a group satisfying A square is equal to identity for all A is the element of a G, then G is abelian. So because A square is equal to identity, if A for all A is the element of a G, if A is the element of a G, then every element has a inverse because G is a group. So if A is the element of a G, then A inverse is also A is the element of a G, then A inverse is also the element of a G. So A square okay, this can be written in the form of a square is equal to identity. We can write A is equal to identity. Then we have a for all A. This is true for all A is the element of a G. Then we can write A inverse A is equal to A inverse E, and then we have to using the associative property A inverse A is equal to A inverse by the using the identity property. This is EA is equal to A inverse. Then we can say that A is equal to A inverse. So we say that every element has its own inverse. Whenever A square is equal to A square is equal to E, then every element has its own inverse. For only A belongs to A is the same as A inverse. This is clearly we have to show that every element has its own inverse. Now we have to show that this G is abelian. So if G is abelian, so if every element A is a inverse, so take A and B as the element of a G. So if A or B are the element of a G, then A inverse is equal to A and B inverse is equal to B, and A, B are the element of a G. So A, B, the product composition of A and B is also belongs to the G by the closure property of a group. So if A and B are the element of a G, then A, B inverse is also equal to A, B there. So we have these conditions are there. So we can prove that AB is equal to BA. So we can say that AB can be written as a form of A and B inverse, and now using the property of A inverse, we can say that this is equal to B inverse, A inverse, and then B inverse is equal to B and A inverse is equal to A. So this means we can show that AB is equal to B of A. Then clearly this group is G is a abelian group is there. So whenever group G satisfies the property A square is equal to E, then G is abelian. So if A square is equal to E, then we have clearly understand that means every element has its own inverse. So now we have to this I just take in the simplified way. So we have to move right to another problem that's saying that if in a group G, then if a group G is abelian, then AB to the power n is equal to A to the power n, B to the power n for all AB belongs to G and for every positive integer. So we prove that, try to prove that AB to the power n is equal to A to the power n, B to the power n for all positive integers. So we can show that AB is equal to BA. Simply this and this condition is given. So let us start with this is true for all positive integers are there. At G be a group, so we take any two elements A, B belongs to G. We prove the result by again by using the induction. So result is obvious for true for n is equal to 1. If AB to the power n is A to the power n and B to the power n, so you can say that result is hold for and AB is equal to BA. So we can say that G is abelian is giving. So this is AB is equal to is this true is simple, not a problem with this. We have to for result, assuming the result is true for n is equal to m, so A to the power m is equal to AB whole to the power m is equal to A to the power m and B to the power m in this way. So now try to solve that this result is true for each and every for n is equal to m plus 1. So let try for A to the power m plus 1. So A B to the power m plus 1, and then we have to A B to the power m plus 1. So this can be that is a m plus 1 times of AB. We AB, and then we can write into this form m plus 1 times. Now we have to using the associativity condition for the group. We can write A, and this is combined by this BA. Then we have a BA, and then so on. So this is we have to going to this way. This is we have to getting simply the m times. So if this is A, BA, 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 we have to getting the m times, and then so if this is giving the m times, so A, BA to the power m and to the into B is there. And because group is giving you abelian, so AB is equal to BA, so AB to the power m and then by using this conditions, we have to assuming that ab to the power m is equal to a to the power m, b to the power m. So the result is true for n is equal to m. So by using this condition, so we write in the form of a to the power m, b to the power m, and now we have to again the using the associativity here. So we have to just writing this a to the power m plus 1 and b to the power m plus 1. So for all positive integers, we have to say that in the case of this result is hold for n is equal to m plus 1. So the induction is completed, and we can say that the result hold for every positive integer. Now by this result, that is a naturally question comes into the mind, the above result, can the result is true for non-abelian group? If we, because we have to proving this result, we assuming that G is abelian in the case. So if G is not an abelian, suppose there G is any group, not we cannot restriction of the abelianity is there committed to it conditions. So we assuming that G is any group. So what we can say, if G is a group, then this condition is hold or not. The above result is does not hold for a non-abelian group. So this is true only for abelian group. Now we have to provide you an example where you can check that easily that this result is not true for a non-abelian groups is there. For example, I take a G is a GL2R with the set of all 2 by 2 non-singular matrix, or over the set of a real number. We take GL2, we already in the group we have to prove that this is a group under multiplication, and this is a non-abelian group. GL and R we have to already prove in the group when we solving the examples of a group, and then we show that this under multiplication, this is a non-abelian group. So clearly this GL2R, if we take a all invertible matrices are there, determinant is not equal to 0 collection, and this is a clearly we know that this is a non-abelian group. So now we have to check the condition, this is the condition is satisfied or not. We have to taking the A is this form and B is equal to this, and clearly you can see this is a non-abelian group, and then AB ka whole square clearly not equal to A square B square. So if we take A and B product of AB and then take a square of this, and A square and B square we have to calculating into this form. So we can say clearly this A or B are the elements, this condition is does not satisfy because this group is a non-abelian group is there. So this result for this result A to A B to the power n is equal to A to the power n B to the power n is true only when the G is an abelian group. If G is does not this group, this result is does not hold in the case of a G is a non-abelian group. This is the one of the examples of we have to send to this form. Okay, now we have to just move the similar types of another problem. If G is a group and AB are the two elements of a G satisfying the condition AB to the power I is equal to A to the power I B to the power I for 3 consecutive integers I, then G is abelian. Now we have to go into reverse way. First in the positive integer is G is abelian, then AB to the power n is equal to A to the power n B to the power n. Now here we have to just try to say that if we have a condition is satisfy AB to the power I, A to the power I, B to the power n for 3 consecutive integers I. So then G is abelian. So let's try to solve this, because he's saying that is true for 3 consecutive integers. So we assuming that first the 3 consecutive integers, let n plus 1 and n plus 2 with 3 consecutive integer for which the given condition is hold. So for which means this condition is hold for 3 consecutive integers. So first one is AB to the power n is equal to A to the power n and B to the power n. This is the first condition we have to say that, and then we have to just say that another we have to just say that AB to the ab to the power n plus 1 is the same as a to the power n plus 1 and b to the power n plus 1, and then we have a to b to the power n plus 2. So a to the power n plus 2, b to the power n plus 2. So we just assuming that this condition is hold for 3 consecutive integer into this signal is hold. Now we have to try to show that this G is a group. So from equation number 3, ab to the power n plus 1 is a to the power n plus 1 and b to the power n plus 1, and then you can say that a to b to the power n plus 1 can be written as ab and ab to the power n, and in the right hand side we have to just say that we have a to the power n plus 1 and b to the power n plus 1. This can be written as a to the power n and b to the power n. And now by the given condition ab to the power n is the same as by the second condition is saying that this can be written as a to the power n, b to the power n, and a to the power n, b to the power n. And now we have to apply the cancellations law. So we have a b a to the power n is equal to a to the power n is equal to b. So we have to apply the cancellations law here. So we just say that this is equal to in this form. We can write into this form. We have to assuming that is a both the cancellations law. So a b c, and then we can say so b a to the power n and a to the power n into b. Okay, so by the equation number fourth is saying that like this. We have a equation number 4 is saying that a to the power n plus 2. We have a b to the power n plus 2 is equal to a to the power n plus 2 and b to the power n plus 2. So this can be written in the form of ab to the power n plus 1, and this right hand side a n plus 1, b n plus 1, and now by the condition of a third we can say that this is a to the power n plus 1, b to the power n plus 1, and then a to the power n plus b to, again using the cancellation property we can say that b to the power n plus 1 is equal to a to the power n plus 1, b is there. So previously we have to show that this condition b to the power n. So we already show that b to the power n is equal to a to the power n b, and here we have to show that b to the power n plus 1 is the same as a to the power n plus 1 b. So we have to write this in the form of this b to the power n into a, and this can be written a to the power n into a, and a to the power n ab, and we have to just write the it, and this one is b to the power n is the same as a to the power n. We have a b to the power n can be written as a to the power n b. So this one is equal to from this we have a and b and a to the power n into b, and again by the cancellations law as a whole we can say that ab is equal to ba. So therefore G is abelian. So if ab to the power I is equal to a to the power I, b to the power I for 3 consecutive integers, then we can say that G is abelian. We can easily prove that. So we have to if this the same problems we have the conclusion of the problem does not follow if we assume the relation for just 2 consecutive integers. So it's saying that we have to provide one counter example in this case where take a certain satisfy this condition for 2 consecutive integers, but the group is not an abelian. So we take a quaternion group of G, and this G is this is under multiplication from a group, and then you know that this group is under this, and this is satisfy these conditions are there. So we have to say that ab to the power let G be a non-abelian, clearly G is non-abelian group. now it can be verified a to the power for two consecutive integer 4 and 5, I is equal to, we have to take a 4 and 5, so ab to the power I, a to the power I, b to the power I for n, but is this satisfy for these two conditions? Let us try, we have to just check this. For example, I to the power 4 can be written as I square ka whole square and then is equal to 1, j to the power 4 is equal to 1, so I to the power 4, j to the power 4 is equal to, we have a 1, and similarly we have to ij to the power 4 is equal to, this is again 1, so we have to set ij to the power 4, I to the power 4, j to the power 4 is equal to 1. Similarly we have to take these two are the same. Similarly I to the power 5 is equal to I, and similarly j to the power 5 is equal to j, so I to the power 5, j to the power ij is equal to k, and then if this is equal to again k, so we can say that ij to the power 5 is equal to j to the power 5, I to the power 5 into j to the power 5. So for I and I is equal to 4 and 5, this satisfy these conditions, but clearly this G is a not an abelian, is a non-abelian group. So now we have to try to discuss some problems of relating to the basic properties of a group. So we have to I have to stop today here, and we have to continue into the next class some more problems of group theory to discuss into the next class. We have to continue some more problems, and then after this we have to complete this portion of a group. So then we have to move to the next section into a subgroups like this. So thank you. I will stop here for the today's lecture, and next lecture we have to try to solve some more examples, problems of this thing. Thank you.